So, welcome to our next lesson. In this lesson, we are going to look at complex numbers first. And complex numbers is an extension of the real numbers. So, you start with your natural numbers, the integers, then the rationals, then the real numbers, and then finally the complex numbers is the largest number collection that we are going to use. So where did these complex numbers came from? They came because people were trying to take square root of -4. They can take square root of +4. We can take for real numbers the square roots, but not for negative numbers. So when we have negative numbers, we can write this. Any negative number can be written as a -1 times a positive number. So the positive number can have the square root that we can find using a calculator, but the negative numbers, the square roots, you can do that. So this square root of -1 is called I, that stands for imaginary, and I times 2, which we usually write 2I because we generally write numbers before letters. So I is the square root of -1. It's unfortunate that this terminology came as saying imaginary or complex. Those are words with negative connotations. They are actually not complex or imaginary. They are quite sensible as far as mathematics are concerned. If I can take square root of +4, hey, I want to take square root of -4 as well, and I want to be able to define that. So for a mathematician, those terms, complex or imaginary, we should have had better, nicer names for them. They are actually really useful and have many applications in mathematics. Anyway, so in general, a complex number looks like a plus bi. So it has two parts. A is written REZ, so that's a real of Z. It's called the real part, and B is the imaginary part. So a complex number comes in two parts. That's not unusual. You have seen this before. If you look at a rational number also comes in two parts with a denominator and a numerator. So a rational number will also have two parts, right? And a complex number also has two parts. The first part we generally write the real number part, and then with the other one with the I. So here are examples of complex numbers: 2 plus 3i and 2 minus 7i. 2 and 3 have to be real. A and B are real numbers, and I is the imaginary number that we have. This number I is interesting. It's the square root of -1, but if I square that, then it's -1. So though I is an imaginary number, its square is a real number. That again is not unusual. You know that square root of 2 is irrational, but when I square it, it's a rational number, which is 2. So sometimes when the squaring brings it out from one collection to another collection. So I is imaginary, it's complex, but I square, if you want, you can think of it as a real number as well. And then if I look for I cube, that's again imaginary, it's -I. And if I look for the fourth power, by squaring that, then I4 is equal to 1. And that's something that we need to keep an eye on. So those are complex numbers. So what do we do with complex numbers? As usual, the same things that we have been doing all throughout this course. We want to define the algebra. We want to add, subtract, multiply, divide, square root. That's what we do with numbers. So with complex numbers, we do exactly the same. So if I have two complex numbers, a1 plus ib1 and a2 plus ib2, I can add them. It's straightforward, obvious. I add the a's together plus I and the b's together. So you add similar terms, and there you are. I can subtract, same thing, and I can multiply. And when I multiply, if I want, I can collect terms. And when I multiply, you will have to use FOIL and get your 4 terms in multiplying this out. But you will also get an I square in the last term, and we already know I square is -1. So you can use that and get it into this form, which is in the standard form of the complex number. I can also divide. Of course I need to divide, and I must have Z2 is not equal to 0 for division. And I can divide any two complex numbers provided that the denominator is not 0. And that's what you get. If I want, I can put it into standard form by applying a little trick, a little makeup if you want. I can bring it into standard form like this, AE plus BI form. All I need to do is to multiply the denominator by what's called the conjugate. So if you have A2 plus IB2, then I don't want this I in the denominator, I can get rid of it. It's similar to the process of rationalization. You must have seen if you have a irrational number in the denominator, like root 2, you can multiply both the numerator and denominator and clear the denominators of irrational or radical expressions. So same thing here. If I multiply the denominator by what's called the conjugate, A2 plus, if I have A2 plus IB2, I multiply by A2 minus IB2, I multiply both numerator and denominator, and then a little simplification will bring you into the standard form. So this will be your A plus I, that will be your B, where A is a real number and B is a real number. So using these operations, I can do all these operations on complex numbers. Let's look at a few examples. So here are some examples. So suppose I have two complex numbers, Z1 is 3 plus I and Z2 is 2 minus 7I. Then I can add them. I add the real parts together and complex parts together to get that. I can subtract and I get that complex number. I can multiply. If I multiply, I have also simplified here and got my I square. I square is using I square is negative 1 somewhere here. I square is negative 1. I use that as well. And I can also divide, and I can either leave it like this or bring it into standard form by multiplying by the conjugate and then simplifying, and I can divide two complex numbers. So complex numbers form a field in that you can add, subtract, multiply, divide and do all operations. These are operations you can't do with natural numbers or integers, but in complex numbers I can add, subtract, divide, multiply and do all my operations. So the conjugate of a complex number I want to define now. If you have A plus IB is your complex number, the conjugate is written with a Z bar like that, and it's defined to be A minus IB. So essentially you change the sign of your I. If you had plus I, then it should be negative I. If you had negative I, obviously the conjugate will be the plus I. So you just change the sign, positive negative sign of the I part, and then you have your conjugate number. So there are some properties of the conjugate number. If I add the two conjugate numbers, then you can just see if I just add them, I get twice A. If I subtract, it becomes pure imaginary. So when I add two complex, the conjugate to itself, the answer is a real number if you want. If I subtract, it becomes pure imaginary. And I can multiply, I can divide and get various connections. So there are many other connections between the complex number and its conjugate, and they are all easy to show, easy to prove, and I'm going to leave